Today we're going to be talking about the mean value theorem. And our mean value theorem for derivatives is if f of x is continuous at every point of the closed interval a to b and differentiable at every point on the interior, so I'm differentiable at the endpoints, I'm differentiable for everything in the interior, and I'm continuous, so those are two key things you want to keep in mind here. We're continuous and we're differentiable. Then there's at least one point C where our derivative at that point equals the slope of the secant line. So keep that in mind. So the derivative at some point equals the slope of the secant line. So let's do a visual example, and I have a visual example down here. So I have our curve, and let me name our curve f of x. So we have our curve, and I have the secant line drawn in, the line through the two endpoints. And my function is continuous and differentiable for all the points from a to b. Now what I'm going to do is we have that same line, so that same line, same slope. That slope looks like it's going to be about right there, maybe a little bit further down. That's this point C is where our derivative of slope of the tangent line equals the slope of the secant line. Okay, so a application of this, or how we're going to be utilizing this. So verify the hypothesis of that mean value theorem. If we do satisfy the hypothesis, then we find a value C that satisfies the conclusion. So remember, you have to verify the hypothesis, which is that our function is continuous and differentiable. So our domain restriction on this curve, that's a half of a circle. So I am continuous and differentiable on this interval. So f of x is continuous and differentiable on the interval. So we have to find the slope of the secant line. So we have to find f of -5, which is 0, f of 3, which ends up equaling 4. And you have to find a point where the derivative equals the slope of the secant line. So our slope is 4 minus 0 over 3 minus a -5. And that's going to equal 1/2. Our derivative at some point C is this equation, 1/2 25 minus x squared to the -1/2 power. Don't forget the derivative of the inside, that's -2x, or 2c, because I've changed my variable. I'm looking for some c. So now, set your derivative equal to the slope of that secant line. So I have 1/2 equals, now do some simplifying, so the 1/2 and the -2 cancel to just be a -c on top. I have the square root of 25 minus c squared on the bottom. I cross multiply. I square both sides, so I get 4c squared is equal to 25 minus c squared. And going through this math, and we have a positive and negative root 5. And both of those are along our interval. If one of these wasn't along the interval, you cancel that one out. But roots positive and negative root 5 are both of the points that are on my interval. So we are done there. Our next example, let f of x equal the square root of 4 minus x squared. And we have 2 points. We're trying to find the equation of the secant line of AB. Okay, so let's do a little math here. F of 0, when I plug in 0, I get 2. When I plug in 2, we get 0, so I need to find the slope between those points. So I do 2 minus 0 over 0 minus 2. That ends up being a negative 1. Pick one of your points. Y minus y1 equals m times x minus x1. If you look at it like this point right here is technically the y-intercept. So I would have 0, and I would have 2. So really, I didn't have to write it in point-slope form. I could have regularly just written it in slope-intercept form, because we knew that that point here was the y-intercept. Now we need to write the equation for the tangent line to f on the interval that is parallel to AB. So I have my secant line here, AB, where this is the slope. So I need to write the equation of the tangent line. So that's using our mean value theorem. Since this function is continuous and differentiable over our interval from 0 to 2, we know that I'm going to have a tangent line that's parallel to this secant line. So I have the same slope. So my derivative, and not all your functions are going to look like this. I just chose two that looked very similar to each other. All right, so I set my derivative, which is negative x over, I forgot my negative 1/2 there, square root of 4 minus x squared equal to a negative 1. I cross multiply, so I negative square root of 4 minus x squared equal to negative x. I square both sides. I'm going to move that work over here. Okay, so a plus or minus root 2. Now, again, we're looking for just numbers along our interval of 0, 2. So the negative version isn't on the interval, so I'm just looking for square root of 2. So y of y minus y1 equals, same slope since I'm parallel, x minus x1. Plug in root 2 into your original function to get your y-coordinate out. And it's kind of cool because when you plug in, your y-coordinate is also root 2. Okay, our next example. An automobile travels 4 miles along a straight road in 5 minutes. Show that the speedometer read exactly 48 miles per hour at least once during the trip. So, what you're given here is you're given 4 miles in 5 minutes. We need to show that the speedometer read 48 miles per hour. Well, that's a speed, or the absolute value of velocity. So, thinking about this, since velocity and speed are continuous and differentiable, our mean value theorem applies. So our average rate. Okay, well, let's look at this. At our position at 0 is 0 miles. Our position after 5 minutes is 4 miles. So let's find this rate. 4 minus 0 over 5 minus 0. So I went 4 miles in 5 minutes. Now we need to show that our velocity, or our speedometer, which is speed, showed exactly 48 miles per hour. So I need to multiply by 60 minutes in 1 hour, and simplifying that, we get 48 miles per hour. Okay, so then writing me a little bit more here. By the mean value theorem, the car's instantaneous speed must be equal to the average speed during the interval. And that's an application of our mean value theorem. As we start reviewing for the AP, we're going to see a lot more examples of these, but it gives you a good idea of where we're going to be using our mean value theorem. Please make sure your lesson summary is submitted on time for me.